So what happens when a huge Hollywood star goes on the world's biggest podcast and challenges the very laws of math and physics? And what happens when probably the most famous astrophysicist alive decides to respond? Well, let's dive in. This whole story is about fame, some really big ideas, and, the messy, sometimes tough process of figuring out what's actually true.
And it all kicks off with this. The actor Terrence Howard is on the Joe Rogan Experience, and he calls out Neil deGrasse Tyson by name. And just like that, a private debate that had been quiet for almost 8 years suddenly explodes into the public spotlight for everyone to see.
But to really get what's going on here, you have to understand this isn't some newfangled social media beef. Nope. The roots of this story go back nearly a decade.
That's right, 8 years ago. That's when Terrence Howard sent Neil deGrasse Tyson a 36-page document that laid out his brand new theories. But here's the most important part of the backstory. NDT actually asked for it. He'd heard Howard was really into science and, out of real curiosity, he invited him to share his work.
So here's the play-by-play. It starts as this private exchange, right? NDT gets the document, reads it, gives his feedback. Then, pretty much radio silence for 8 years. And then bam, it all blows up on this massive public stage, which basically forces NDT to finally go public with his side of the story, and to reveal what was in that original critique he sent.
So how exactly did NDT handle this 36-page document? Well, he didn't just laugh it off or toss it in the trash. He actually gave it the kind of serious treatment you'd give a formal scientific paper. He gave it a peer review.
And this is such an important way to think about peer review. It's not supposed to be an attack. It's a duty. It's how science stress tests new ideas to see if they hold up. Your colleagues have a job to do, and that job is to try and find the flaws, not to tear you down, but to work together to get closer to the truth.
And NDT followed this process to the letter. He read every single page. He used his professional knowledge to critique the claims, literally marking up the document with red ink, just like any scientist would for a colleague. And he said he did it all out of respect for the obvious time and effort Howard had poured into it.
Now, this whole back and forth really shines a light on a super fascinating quirk of our own brains, something NDT brought up himself. You ever wonder why sometimes we can feel so incredibly confident about something we actually know very little about? Well, the answer might just be something called the Dunning-Kruger effect. So the basic idea is this. Knowing just a tiny bit about a complex subject can give you a really dangerous level of confidence. You know just enough to feel like an expert, but you don't yet know enough to see the giant ocean of things you don't know. It's only when you learn more that your confidence takes a nosedive before it can climb back up, this time based on actual knowledge.
And this chart just illustrates that journey perfectly. You start out as a total novice, but you're way up high on what they call the peak of Mount Stupid, just full of unearned confidence. Then, as you actually start learning, you plummet down into the valley of despair. That's when it hits you just how much there is to know. It's only after a lot more work that you can climb back out onto that plateau of real, sustainable expertise.
All right, so let's get down to the nitty-gritty. What were the actual claims in that 36-page document that Neil deGrasse Tyson had a problem with?
Okay, so this was a really foundational point in Howard's paper, that 1 times 1 should really equal 2. His logic was that if you multiply something by itself, the result should always be bigger. But, as NDT pointed out, that whole idea falls apart the second you look at a huge group of numbers, all the ones between 0 and 1. Take 0.8 times 0.8. You get 0.64, which is smaller. And NDT argued that this one simple fact unravels a lot of the logic that comes after it.
All right, here's another one, based on a little thought experiment. And it kind of feels like it makes sense, right? You put a candle in front of a mirror, you see 2 flames, so you should get double the light. But physics says not so fast. NDT explains that first off, no mirror on Earth is 100% reflective, so you're already losing some light. And second, the reflection you see is actually further away than the real candle, so its light is weaker by the time it hits your light meter. The reading is always going to be less than double.
Now, a really common argument you hear from people with unconventional ideas is that all the great geniuses in history were misunderstood and rejected at first. NDT pushes back on that with this killer line. Look, just because people don't understand your idea, that doesn't automatically make you Galileo.
And this same thinking applies to these historical figures. Howard held up people like Nikola Tesla as these misunderstood geniuses.
And NDT actually says, yeah, of course Tesla was important. We literally named a unit of measurement after him. But he also makes the point that a lot of Tesla's later work was pretty out there. And for these other guys, like Walter Russell and John Keeley, the real problem is that their work just doesn't have experimental support, and other people can't reproduce their results. And those two things are the absolute bedrock of all science.
So this all brings us to the biggest lesson in this entire saga. It's not really about one person being right and another being wrong. It's about the process. How does science actually move forward, especially when it's faced with ideas that sound, well, completely crazy?
And this is so important to remember. Science isn't about shutting down crazy ideas. Honestly, some of the greatest breakthroughs in history sounded totally nuts at first. But for a crazy idea to become an accepted fact, it has to go through the gauntlet. It has to survive some seriously tough testing.
I mean, just look at continental drift. The idea that whole continents are just sliding around on the Earth's surface was met with huge skepticism. And why? Not because scientists are just stubborn old-timers, but because there was no good explanation for how it could happen. But then, evidence started showing up, matching fossils on different continents, things like that. The final nail in the coffin was mapping the mid-Atlantic ridge, which gave us the mechanism. The seafloor was literally spreading. It was hard evidence, not just a cool idea, that turned this crazy theory into textbook truth. And then, of course, there's the ultimate example, Einstein. His idea completely turned physics on its head, suggesting that space and time themselves could bend and warp. So how did it become accepted? Simple. It followed the process. It got published in a peer-reviewed journal, it was backed up by stunningly beautiful math, and crucially, it made a prediction you could actually test, that starlight would bend around the sun. And when that was proven true during an eclipse in 1919, the game was changed forever.
And really, this is the bottom line. NDT's main point is that the right place to debate these things isn't on a podcast or on social media where ideas can't really be properly examined. It's in research journals, where other experts in the field can give them the deep, critical, serious attention they deserve. In science, that's the highest form of respect you can possibly pay to a new idea.
So this whole affair leaves us with a really big question to think about. It's absolutely essential to have an open mind and to challenge what we think we know. But at the same time, science demands we be incredibly skeptical and insist on proof. So the real challenge for all of us is to find that perfect balance, to be open to revolutionary ideas while also holding those ideas to the absolute highest standard of evidence.